Look up at the night sky. What do you see? A vast expanse peppered with stars. These stars are massive balls of burning gas like our sun. Some stars exist alone, while others cluster together in gigantic groups called galaxies. Our sun, a rather average star, resides in a galaxy we call the Milky Way. But where did all this come from? The answer lies in an event called the Big Bang. This theory suggests that the universe originated from an extremely hot, dense state and has been expanding ever since. Join me as we embark on this fascinating journey through time and space, unraveling the secrets of the cosmos. Imagine a universe completely different from what we know. No stars, no galaxies, not even space itself. Before the Big Bang, there was no time, no space, and no matter as we understand them. All the energy and matter that make up our universe today were concentrated into a single point, infinitely small and dense. This point, often referred to as a singularity, contained the potential for everything that would become our universe. Think of it like a seed containing the blueprint for a giant oak tree. Similarly, the singularity held the potential for the universe as we know it, waiting for the right moment to burst forth. The concept of a singularity is mind-boggling, pushing the limits of our understanding of physics. As we continue to explore the universe and gather more data, our understanding of its origins will undoubtedly become more refined. Around 13.8 billion years ago, the universe as we know it began. The singularity underwent a dramatic transformation, an event we now call the Big Bang. But the Big Bang wasn't an explosion in the traditional sense. It was the rapid expansion of space itself. Imagine the surface of a balloon being inflated. As you blow air into it, the surface stretches and points on the surface move away from each other. Similarly, during the Big Bang, space itself expanded, carrying energy and matter along with it. In the first fraction of a second, the universe underwent a period of exponential expansion known as inflation. This rapid expansion smoothed out any initial irregularities, much like stretching out a wrinkled fabric. It also determined the large-scale structure of the universe, laying the groundwork for the formation of galaxies and galaxy clusters we observe today. As the universe expanded and cooled after the Big Bang, energy began to transform into matter. The universe was filled with a hot, dense soup of elementary particles like quarks, electrons, and their antimatter counterparts. Over time, these fundamental particles began to combine, forming the first protons and neutrons. This process, known as Big Bang nucleosynthesis, lasted for just a few minutes but was crucial in determining the composition of the early universe. These light elements, forged in the fiery furnace of the Big Bang, would become the building blocks for everything else in the universe. After the formation of the first elements, the universe entered a period known as the Dark Ages. This era, lasting for hundreds of millions of years, was characterized by darkness because stars had not yet formed. Gravity caused slight variations in the density of this primordial gas to grow. These denser regions attracted more matter, pulling it in with their increasing gravitational pull. As these clumps of gas collapsed under their own gravity, they heated up. The pressure and temperature at their cores soared until nuclear fusion began. The first stars were born, burning brightly for a few million years before exploding as supernovae. These explosions scattered the heavier elements forged in their cores into space, enriching the surrounding gas clouds. As more stars formed, they began to cluster together under the influence of gravity, forming the first galaxies. These islands of stars came in a variety of shapes and sizes. Some were spiral galaxies like our own Milky Way, with graceful arms of stars, gas and dust. Others were elliptical galaxies, more rounded and lacking the distinctive spiral structure. Galaxies collided and merged, shaping each other and triggering bursts of star formation. Over billions of years, these interactions sculpted the universe into the intricate web of galaxies we observe today. Within these galaxies, new generations of stars were born from the enriched gas clouds left behind by the first stars. While stars were igniting and galaxies were taking shape, the universe itself continued to expand. This expansion, a key prediction of the Big Bang theory, was first observed by astronomer Edwin Hubble in the 1920s. Hubble noticed that the light from distant galaxies was stretched. Its wavelength shifted towards the red end of the spectrum. This phenomenon, known as redshift, is analogous to the Doppler effect we experience with sound waves. Hubble's observations provided the first direct evidence that the universe was expanding, with galaxies moving away from each other. He found that the farther away a galaxy was, the faster it appeared to be receding, a relationship now known as Hubble's law. This discovery revolutionized our understanding of the universe, showing it had a beginning and was evolving over time. The expanding universe became a cornerstone of modern cosmology, supporting the Big Bang theory. In the 1960s, astronomers made another groundbreaking discovery, the cosmic microwave background radiation, or CEMB. This faint afterglow of the Big Bang permeates all of space. Think of it like the heat left over from a campfire. Even after the flames have died down, the embers continue to radiate heat. Similarly, the CMB is a remnant of the Big Bang's incredible heat, a faint echo of the universe's fiery birth. The CMB was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely through the universe for the first time. The CMB we observe today is that ancient light stretched and redshifted by the universe's expansion over billions of years. By studying the subtle temperature variations in the CMB, cosmologists can learn about the conditions in the early universe and gain insights into its composition, geometry, and evolution. The Big Bang Theory paints a compelling picture of the universe's history. It tells a story of a universe born from a state of unimaginable density and heat, expanding and cooling over billions of years. From the first moments of the Big Bang to the formation of the first stars and galaxies, our understanding of the cosmos has been shaped by scientific inquiry and technological advancements. But the story of the universe is far from over. The universe continues to expand, and the fate of this expansion remains one of the biggest mysteries in modern cosmology. Will the universe continue to expand forever, growing colder and darker, or will gravity eventually halt the expansion, causing the universe to collapse back in on itself in a big crunch? As we develop new telescopes and instruments, we peer further back in time, closer to the Big Bang, seeking answers to these fundamental questions. The journey of cosmic discovery continues, fueled by our innate curiosity and our desire to understand our place in this vast and awe-inspiring cosmos.